Hello and welcome to today's seminar in the Smart Mobility Connection series. My name is Carly Benhart-Kukula and I am the 2019 Women in Transportation Fellow. The Smart Mobility Connection series is sponsored by the Traffic 21 Institute and the Mobility 21 University Transportation Center as an opportunity for faculty to showcase their current transportation projects. It is also an opportunity for students, fellow faculty, deployment partners, and the broader community to engage and network with researchers, highlight opportunities for involvement, and foster future interdisciplinary collaboration. Please note this session is being recorded and all participants' microphones are muted. To ask a question, please send a message through the chat box. You do not need to wait until the end of the presentation to send your questions. Now I would like to introduce today's speaker. Mark McCord is a professor of civil engineering and city and regional planning at The Ohio State University, where he has been teaching and conducting research in transportation systems, engineering, and planning since 1983. His recent research focuses on innovative uses of remotely and automatically sensed data for transportation applications. Professor McCord is the co-founder and co-director of OSU's Campus Transit Lab, a living lab that supports research, education, and outreach. He received a PhD in civil engineering and transportation systems from MIT, an MS in industrial engineering from Stanford University, and a BS in civil engineering from Purdue University. Please help me welcome Professor Mark McCord as he tells us about his University Transportation Center project, time of day traffic volumes using video imagery obtained from transit buses in regular operations. Professor Mark McCord will be presenting, and this project is co-authored by Mark McCord, Rabbi Michelani, and Benjamin Koifman. Thank you.
Thanks, Carly. Hello, everyone. Depending on where we are, good afternoon or good morning. There we go, so I can share it now, right? Good. All right, whoops, sorry. What happened here? There we go. Okay, thanks. Sorry for that. Rabbi Michelani, Ben Koifman, and I are grateful for the invitation to be able to present our efforts involved with taking video from transit buses while they're providing their regular transit service. The videos are taking, the cameras are taking video for other purposes, but they see vehicles. We take the vehicles, try to turn them into traffic volume estimates for sort of recurring patterns, so sort of planning level estimates, not real time at this point. Our focus at this time is sort of time of day patterns in the traffic. Our present effort right now is we've developed an approach that basically estimates traffic volume from this mobile platform. And the present efforts right now are to look at the performance of this approach we've developed using real video, try to refine it, and also demonstrate the potential for a viable tool to get traffic volumes across extensive urban networks in the future. I've organized this presentation to give you sort of a quick motivation for what we're doing, to set the concept that we're presently working under, briefly touch on the methodology that we use to take the video and convert it into traffic volume estimates, and then sort of give empirical results we've collected, or at least some of the empirical results we've collected in what I call a multifaceted empirical study. We'll see why it's multifaceted when we get there a little bit later. And then finally, I'll discuss where we see ourselves now and where we see ourselves going with this in sort of the near future. By way of motivation, let's just sort of accept sort of like as a postulate that traffic volumes are used for a variety of engineering and planning purposes in urban areas. And the traditional way we go out and get traffic volumes is, we like to call them fixed location sensing. Whether we send our students out over here on the left to sort of sit there and count vehicles as they pass, or click on vehicles as they pass, or we put road tubes down on the right, we're talking about going to one segment, one location, and getting the vehicles through time as they pass. So the idea is we're out there at one location and we're getting vehicles through time. And we get pretty, obviously, good estimate, good data on how many vehicles pass that location in time. But our resources are limited when we're talking about an extensive urban network. And this is just the OSU bus network. And the idea we're trying to illustrate here that buses, on the other hand, are looking all over the network. These guys, where we're putting down road tubes, can be one or two places on this network, and they're missing all the other segments of the network, whereas buses cover the entire network. They do so on a regular and repeated basis, and that's going to be sort of key to what we do in our recurring traffic patterns. So the concept we're working under now is we want to take advantage of this repeated, extensive coverage of transit vehicles while they're out there, to observe, in quotes, we'll see what that means in a minute, to observe the traffic on the major roadways in an urban area. Let me sort of piece this along. This repeated coverage, I said the traditional way we get traffic volumes, we go out there, think of it as counting or putting a road tube down, and we get data all through time. We get this long, hours and hours of data at this one point. The bus, for example, with its video sensor on, goes by and it's going to see what's happening in a very short duration. So any single pass of a transit bus is going to give us a very short duration observation of the traffic. But because buses go around again and again, cycle after cycle, multiple buses, day after day, we get lots of these repeated short duration observations. And the hypothesis is we can aggregate them to come up with a good estimate of what's the typical pattern out there. Because it's ongoing, buses go out there day after day after day, we'd also have the ability to sort of look through time. When we put road tubes out there, we put them out once in a while, maybe we come back several years later and do that. We don't see what's going on in between. Because we have this ongoing coverage from the transit buses, because they're providing another service, but they're out there anyhow, time after time after time, we can monitor through time. Next, we like to say they're covering most of the major roadways in an urban area. Buses travel on the roadways that are of most interest in terms of traffic data. And so we're really getting spatial coverage, which we've never had before from traditional ways of doing traffic monitoring. And then similarly, because the buses are out there for other purposes, we don't have to pay for the platform. So there's little, I always like to say no, but then my colleagues say, there's always going to be some additional costs. But we don't have to pay for the platform. It's out there being paid for because it's providing other service. So we're just piggybacking on the platform. We're not investing in the platform. We'll see with the video, we're not investing in the sensors either. And then finally, transit buses are public service. And so the hypothesis here is that because they're in the public domain, that they would be a little bit easier, less costly to get their data, use it for public service. We're not going to go through some private company that would be selling the data. And then finally, we've been working, we have, as Carly mentioned, what we call the Campus Transit Lab at Ohio State. We've been working in transit for quite a while. Transit is a very valuable service, but we all know it's costly and it needs to be subsidized, usually by votes and tax levies that people vote on. So anytime transit can look like what we call a good citizen, in this case, providing information for the general traveling public, that would be good, probably a plus in the overall one transportation system idea. So we started this a while ago. And our concept at the time was to take inexpensive sensors and mount them on buses and get the traffic data. And our first take was to use LiDAR sensors. And it was, we have real good relationships with the traffic people, the transportation and bus operators at Ohio State University. But we weren't ready to start drilling holes in their buses to put LiDAR sensors on. So we equipped the van with LiDAR sensors, drove around campus and off-campus roads, got nice pictures of vehicles, could automatically process the vehicles. We'll get back to that later. That's an advantage of the LiDAR, and be able to sort of test out some of the concepts we started developing. While we were doing this, I call it a happy coincidence. Transit agencies around the world and at OSU, Ohio State University, were putting cameras on their buses for other purposes. Basically, they put them on for safety, security, liability issues. If there's an accident, what happened? If there's someone hijacking the bus, we can see what's going on, etc. So the cameras, it's important to notice, are not put out there for traffic counts. They're up there for other purposes. And it just happened to be this was starting to take hold while we had developed this LiDAR idea of sticking LiDAR on buses. And so we sort of did a right turn here and said, let's change our focus from the LiDAR to cameras, because they're out there. We don't have to put any extra hardware on the buses. They're out there for other purposes. Just as a side note, again, because of our relations with the people that we call transportation and traffic management, who operate the campus area bus service, CABS, I forgot to spell out that abbreviation there, at OSU, they were just starting to put the cameras out there, and we've been working with them on transit projects and giving them information for transit operations for several years. And so they were willing to work with us to configure some of these sensors, at least the angles. We've been using this driver side rear sensor back here that points out. We could get a little better angle. They were willing to work with us with the angle to be able to see the vehicles. Now, that sort of changed our perspective again, from just saying we're going to put sensors on the bus to now our present objective is let's take advantage of the existing video data out there. So as I said in the beginning, we don't have to pay for the platform because the platform's already out there for another purpose. We're not paying now for the sensor because the sensor's already out there for another purpose. Let's try and see if we can get this video, turn them into traffic estimates across our urban roadway networks, and not in sort of a beta test. Let's do it while they're in regular operation and see what we get. So I won't go, in the interest of time, I won't go in a lot of detail into the methodology, and it's not that complex. It's pretty straightforward once you think of it. But the basic idea here is right now we're taking the video and we've developed a graphical user interface where we sit there and basically when a vehicle passes, we click. We've been in parallel, and I'll talk about that later, trying to work on some automatic vehicle detection and processing. But right now, the methodology, the concept is the vehicle passes and we observe by basically getting a frame at this frame, and we know the location of the bus, so we know where the vehicle is at this frame, which can be connected to time. So we know the locations of these observations. Right now, we're doing it semi-manually through this GUI. We hope to make some progress. We are making some progress. We hope to make more with the automatic vehicle detection. But the idea is, as I mentioned in the beginning, traditionally traffic volumes are how many vehicles pass your point over a time, over an hour, over a day, over a 12-hour period. we're not getting vehicles over one specific point through time. We're getting vehicles from what we call a moving observer. The bus is a moving observer, and there's been some textbook talk and some research studies about the moving observer long before they thought about buses and video on buses to sort of detect traffic. And we had to tweak it a little bit because we had to tweak it for a bus going in one direction, traffic going in the other direction. And that's what we said, this methodology we sort of, I don't want to call it develop, but we sort of modified the traditional moving observer method for observing traffic going in one direction, the buses going in the other direction. Looks, again, I'll skip the detail, the real detail. On the right, we're trying to show it in sort of a time-space diagram with trajectories of vehicles this way, the trajectory of the bus going this way. When they cross each other, we get an observation of the vehicle. But over here is what we're trying to predict, trying to illustrate. We think of like an observer, traditional observer. This is supposed to be an eye, by the way. Down here at this point, counting vehicles as they pass. The bus is over in this right-hand lane going northbound. So it's going to see this vehicle up here when it passes, this vehicle up here when it passes, this vehicle up here when this vehicle is coming down this way, the bus is going this way. It's going to observe these vehicles at different locations at different times. To convert it, we basically need to say how many vehicles would have passed this observer in what we call an equivalent duration. And so that duration, again, I'm not going to take the time to really motivate it. Probably could have done it equally fast and talk about not motivating it, but I'll just sort of say that equivalent duration is going to be, can't see my cursor here, but basically the time the bus takes to go northbound in this, and that's going to be the time it's observing these vehicles. And then when it gets off the segment at the end here, there's going to be an event, whether I see a vehicle or whether I see no vehicle. How much time would that event take to pass over here? So again, some of you may see it immediately. Some of you may say it's obvious. Some of you may say it's a bit arcane, but just take my word for it. The approach we're using is the flow rate. The vehicles per unit time is the number of vehicles, this N vehicles, that the bus sees while it's going this way and the traffic's going this way. So how many we count? We get that from our GUI, divided by this equivalent flow rate. And that equivalent flow rate is going to be the time it takes the bus to travel here, plus this, what we call T2, this time for this last event when the bus is just leaving. I didn't see a vehicle or I just saw a vehicle. How long did it take that event to pass downstream? And there are different ways, and that's one of the research areas we're still working on to estimate T2. Right now, we basically take the length of the segment, the length of this segment, and divide by the speed limit to figure out how much time it would take a vehicle to pass here. And that's one of the areas we're refining now. That gives us a flow rate, let's say vehicles per minute, 3 vehicles per minute. Well, what is that per hour? Multiply by 60, I get 180 vehicles per hour. So that's our volume. But that's from one individual bus pass. And the idea is because buses are going over and over again, we aggregate these individual passes to come up with a aggregate estimate of, in our case, the hourly volume. Right now, we're taking averages, but again, there's other ways we're looking into doing that aggregation better. But the basic methodology now we use, vehicles come by, I click it with my GUI. We get the video from Transportation Traffic Management. Sean Roberts works very closely with us and pulls the video when we ask him to pull the video. We get the video, we sit there with our students and click on a GUI. We're working on some automatic processing. Once the GUI gets the information, we can automatically process it with this approach, this equation on the left, to get a volume for any bus pass over a segment. And then we simply aggregate the the individual volumes in various ways. We're just doing one right now today. We aggregate the volumes in various ways to come up with an estimate of a time period. Today we'll talk about hourly volumes. So that's the concept. Let me sort of now give some empirical results. And I call it a multifaceted empirical study because it serves not only for the research component to validate this approach, but we also use it, as a matter of fact, the setting for the empirical results I'm going to talk about next are in sort of a class term project. And then we actually use the results and give them for an outreach component that I'll talk about. So this study, this empirical study I'm talking about, has an education component, a research component, and an outreach. And I'll start with the education just because it sort of sets the data collection scenarios, Rabia Michelani, one of my presenters here, and I co-teach a class called Civil Engineering 5720, Transportation Data Studies. It's an elective course by civil engineers. Some city and regional planners take it. Civil engineers, undergraduates and graduates take it. City and regional planners, graduate students take it. The idea is to look at traditional and emerging data to come up with, how do we collect the data? How do we analyze it? And because of this project, the idea of this, our concept here of emerging data sources, basically bus-based video, turning them into traffic volumes, it fit nicely into this course. And so we developed a term project. This will be the third year this year, where basically we estimate hourly volumes and vehicle miles traveled across campus with traditional approaches that we teach in the class, and then with our bus-based video. And so we do it on a specified day. One year we did it between 7 a.m. and 7 p.m. The next year we took our students and kind of spread them out, and we increased the size of our network. And so we cut down on the time. We did it between 8 a.m. and 6 p.m. But just think of it, it's a day, a time of day, 10 or 12 hours. And we look at the segments on campus, and we try to estimate the traffic volume on these segments by every hour. And there's probably, if I sort of take the number of segments by the number of hours, there's roughly 250 segment hours. We only have a certain number of people in the class, so we spread them out among these segment hours. They go out there and count the cars as they pass at one time, and then go out to the same place or someplace different, count at another time, what we call coverage counts. And at the same time, MORPC, the Mid-Ohio Regional Planning Commission, the MPO for the Central Ohio area, puts down road tubes for us and for them. I mean, they say, Ohio State's a big part of Columbus. Columbus is a pretty big city. I mean, it's like Pittsburgh, and the university is a big part of it. And so MORPC likes to get counts for their regional traffic model, or the regional transportation travel model. And so they say, yeah, we'll work with you if we can put the counts where we want and you want, and we can mutually find a place to do it. It helps that many of the people working there are my undergrad and graduate students, but they're willing to go out and lay tubes down here. So for example, on this network that I'm showing over on the right, the blue segments are where they laid tubes. And so basically MORPC go down and lays road tubes where we get data for, we get them for days, but for this study, we get them for 10 or 12 hours. The students sample by going at different hours across the other gray segments, and then they're going to combine these data with traditional methods. At the same time, on this day of study, OSU, of course, is operating buses all over this network, and we get Sean Roberts and TTM to give us the video. And so we collect about 60 hours of bus video on the day of this study. The students then in the class, we teach ways because it's what we call small networks, but it also works for statewide networks. We have these control counts where we get data extensive data through time. In this case, it's a road tube. But then we go and sample the other segments for a shorter duration of time. And in short, we superimpose the temporal variability we get from the control counts, the road tubes, on these coverage counts where the students are counting the vehicles, and we can estimate what the volumes are for every hour, every segment in the network. So that's what we teach in class, and so they go and get their hands dirty by actually doing that in the class project. But then at the same time, they process the bus videos. They help us with the GUI, so we get a lot of labor to sort of process the bus video through the graphical user interface. So we get the data processed and then run the algorithms that we have are basically moving observer modified algorithm to estimate the traffic flows. And then the students basically get the volumes from these two methods by hour, by 12 hours. They compare them, they look at vehicle miles traveled, they look at little different tweaks that we ask, and we refine this every year. But that's basically the class project. And then of course, they report on it and tell us something about it. And just to give an idea, we started this because of this project back in 2018. This is the network I was showing. We had 6.26 miles, 7 a.m. to 7 p.m. last Thursday in October 2019. We tweaked it a little bit, but we also expanded the network. And that previous year we had 30 students. 2019 we had 32 students. And then in 2020 we're going to do it again. We were going to collect the data yesterday, but it was really raining, and we got MORPC and TTM at OSU to agree to we'll put our big data collection to next week. So we're planning on doing this next week. And if you can see by my pseudo animation, we're adding a few more segments this year. The results I'll talk about are based on the 2018 study. We have results for 2019. They look very similar to what we got for 2018. We just haven't combined them in a way that's user-friendly at this time. So I'll emphasize the 2018 study, which is this network from 7 a.m. to 7 p.m. last Thursday in October. So, as I said, you're not expected to read this. It's small, I understand, but the idea is just get the goal is just to give you the idea of what we have here. These are the road tube segments. And as I said, MORPC, Mid-Ohio Regional Planning Commission, put down road tubes on 5 segments, 2 directions. So we have 10 segment directions here. And the road tubes get volumes. They get them every 15 minutes. But for this study, we combine them into a 7 to 8 a.m. volume. So on segment 2.1, again, I don't think you can, well, I can read it. Maybe you can too. The road tubes said we had 278 vehicles going in this direction on segment 2 between 7 and 8 a.m. Our video volumes, which were obtained by 3 buses passing that during that hour, different routes or the same bus with, can pass the segment twice if the cycle time is short enough. We averaged that and got 275 vehicles. That's the volume in that hour. 8 o'clock, etc. So we do that for every hour. We do that for all the segments with road tubes. And over here, for example, we sort of say, well, what's the 12-hour volume? If I were to estimate what happened from 7 a.m. to 7 p.m., we simply add up these numbers. And so from the video passes, we get the hourly volumes, add those up, and we get a 12-hour volume. On segment 2 in this direction was 5,147 vehicles. The road tube said there were 5,027 vehicles. We do that for all the segment directions where we have road tubes. And rather than just look at them, I gave you 2 numbers there, and one 12-hour and one 7 a.m. Say, hey, that looked pretty good. Let's quantify the differences and sort of look at some performance. So we have what we call the relative difference, where we take the video volume for the hour. subtract off the road tube volume for the hour, or eventually for 12 hours, and divide by the road tube volume. So it's like the difference relative to what you would have gotten from the road tube. And we call it difference rather than error because the road tubes aren't perfect ground truth either. They have errors. Anyone who's worked with road tubes know they're not, they don't get exactly the counts out there. So we just call them differences, but we're using that as the reference to refer against our video volumes. And then we take the absolute relative difference, which is basically the absolute value of this. The RD is going to tell us, is there a bias because the sign, if it's positive, it means the video volumes are getting higher volume. The video data is producing higher volumes than the road tube volumes. If it's negative, it means the road tube volumes are producing higher, as the road tubes are giving us higher hourly volumes than the video volumes. So the RD is giving us both the magnitude and the sign. The absolute value of the RD is sort of giving us, how much error in terms of a number are we making, the magnitude of the error. So here's, our 10 road tube directions from our 2018 study. Again, 2019 study looks very similar. Just didn't have time to really consolidate it. And the first sort of punchline. So this is, for example, on that segment 2-1, if I look at all 12 hours, take my relative difference and average them, I get a 20% error difference, I should say. I get a 2% difference. But I get a 20% difference if I average the absolute values. In this 2%, the positives and the negatives are canceling out. So if I look at these absolute value of the relative difference, this column, and average those, so I've got basically my 120 hours, segment hours, and I take the average of the magnitude of these errors, it's pretty big. It's bigger than I would have expected when we started, especially when we looked at some of those anecdotal observations like that 7 a.m. on the first segment. It's 23%. So it's pretty big. However, the relative difference where we allow the positives and negatives to cancel out is pretty small. It's getting close to zero. The hypothesis here that aggregating over larger periods may allow these positives and negatives to cancel out. And sure enough, if I look at the difference between what I get for a 12-hour volume on this segment direction from the road tubes and from the video, the average magnitude there, it's getting close. It's 12% in this case. When I used to do AADT estimation, statewide stuff, people would often say, hey, if we can get it to 10%, that's pretty good. So we're getting pretty close in terms of a 12-hour estimate. And the point here is we're doing this with only a few bus passes. Some segments, by the way, have very low magnitudes of differences. And we're looking into, that's what we're looking into now. What are the characteristics when this does very well or when it does poorly? If we have time, I can talk about our working hypotheses. But we're also trying, remember one of the concepts here was buses go over and over again. If you looked at that table at the beginning, I said, this hourly pass, we're only getting this hourly volume, 7 to 8 a.m. We're only getting it with 3 bus passes. But buses are going over day after day after day. We can get a lot of bus passes. So we regress the magnitude of this difference as a function of the number of passes and segment lengths. And sure enough, the results are encouraging. As the number of passes go up, the error goes down, the negative sign. As the segment length goes up, which is sort of a longer duration observation, the error goes down. And we're getting significant values, et cetera. And so remember that we're going to get more and more bus passes as we do this if the buses are out there day after day. I was kind of speed through this to sort of leave some time for questions. But in addition to getting the hourly volumes, we're also interested in the vehicle miles traveled. Vehicle mile travel by definition is I sum the travel of each vehicle, how much distance it travels, and I just add those all up. But the way we usually calculate it, we usually get the length of a segment and multiply it by the volume on that segment. and now. So we're going to get vehicle miles traveled in two ways, one with our video data base volumes and one with our traditional base volumes. And I'll skip the motivation, but vehicle miles traveled is the most basic parameter of how much travel there is across an urban network or any network. And basically, if I only looked at the road tube segments and looked at their 12-hour VMT based on the video, I get 9,581 vehicle miles traveled. Traditional from the tubes, 9,221, only a 3% difference. Again, this is because these positives and negatives, and we're getting longer time periods. We're getting very good estimates of VMT from our video-based data, or very good, at least very close to what we would get with the traditional way. Remember, the overall network, we had to get with coverage counts. In the interest of time, I won't go through the methodology again, but there's some assumptions that need to be made. And so we let the students, which are pretty advanced students in engineering, make their assumptions, and their range of what the VMT based on the various assumptions, the different student groups, was between 20,000 and 25,000. The average of their 5 or 7, I think, VMTs was 22,000 across the entire network. We got 23,500, a difference of less than 5%. And to me, even more interesting, based on the assumptions, we're getting a difference of like 5,000, about a 20 to 25% difference here. And our difference is just 4%. So bodes well for getting VMT from the video-based data. Finally, we do this education when we sort of was set in the class. We got these research numbers and sort of precise relative differences from the research study. The outreach component, basically OSU is a large campus, one of the largest single campuses in the world. It has lots of different land uses. In short, it functions like a small city. That's why we call it sort of a living lab. We like to think of it as an urban city. Policymakers are getting more and more interested, not just at OSU, but I'm sure everywhere, with environmental sustainability. They don't have data in terms of monitoring data for VMT. So we provide the VMT we estimate from, now that we're getting in the video VMT looks very much like the traditional VMT. We provide them the video-based VMT is the only sort of quantified data they have, measured data, I should say. They do surveys and say how many miles did you travel, et cetera, but this is quantified. So we call this an outreach function where we provide the university with VMT estimates. I'll just take 2 minutes here to sort of show you where we are, where we're going. Remember, we see this as sort of education, outreach, and research. On the education and outreach study, we're repeating this, the education study, we're repeating the class project. This was the year on the lower left that I talked about. We have the data, we just didn't compile it for today for the 2019. We're getting our data next week, a week from yesterday for our 2020. So we repeat the educational experience 3 times, obviously different students, all of them, no one's repeating the class. We continue to provide the VMT to OSU in the outreach function. On the research side, this was an empirical study. When you do empirical studies, especially first-time empirical studies like this, it's good to repeat them and see if we get the same results. So that's what we're doing. I talked about our 2019 results look very similar. No differences in the punchlines. I mean, maybe our 23% error becomes 24% or something like that, but we're getting very much the same results. Our 12 hours are looking very good. The hourly volumes on their own aren't good yet, but that's because we have a small number of passes. We said we want to determine what's causing the good estimates versus the bad estimates. So we go back and look at the video where we're getting really bad estimates. And basically, as you could guess, when we're getting a really low estimate and the tubes are saying it's a lot higher volume, it's just some random approach that we didn't see any vehicles with this one pass. We think we know how to correct that and work on the methodology. When we're getting the video being a lot higher than what we're getting with the tubes, again, it's, don't quote me on this because it's kind of new, but it looks like that's where queues were backing up on the street, and we're trying to figure out how to handle those. The other thing we're working on is to actually, when I get the data from an individual pass, can I get a better estimate? We talked about, I won't belabor the point or take more time, that it's basically this number of vehicles the bus sees times the time the bus goes this way, plus this estimate of how much time it would take this last observation to get down here. Our T2, we're doing different things with the T2, and we see that some work better than others. We get the values from every bus pass. How do I aggregate the different values? The ones I talked about today, we just took a simple average. We do a weighted average and it looks better. We have other things in mind to improve the estimates. And then the whole motivation for this is, well, let me put it this way. When we go with our GUI and click on this and produce the results, it's probably less time and less costly than doing one traffic study. We can talk about that, but it's even with our GUI. But the motivation for this is that we're going to get this all over the urban network, and we're going to do it through time. And so we need a more efficient way to process the data, and we're working on some automatic vehicle detection. We started discussing with Christoph Mertz and his team over at CMU. We're trying some other things over here. This is a parallel project. This project I'm talking about today is just trying to demonstrate that the approach will work, but then how do we get the data efficiently? So with that, I'll stop and just say that it looks like the results are promising. You can read this. We've been doing this now and extending, again, OSU is a large network. It's still not as large as Columbus or Pittsburgh or Los Angeles or something, but we're trying to demonstrate that this could be used on an extensive network and provide meaningful information. We've got several refinements underway, research and development, but again, we're leveraging, we think it's kind of neat the way we're leveraging this research study by bringing it in the classroom as a class term project, but also taking the values already that we're producing and giving them to the planners and decision makers at the university. So with that, I'll thank you for your attention. Obviously, lots of students who helped along the years on different components. I won't read them out. We want to mention both OSU's transportation and traffic management, who provide us with the video data, and also MORPSI, who goes out and lays the tubes for us. So with that, I'll stop there. Thanks for your attention.
All right, we have a few questions. The first is, how does the method work when the bus is going on a 4-lane road segment with 2 lanes in each direction?
Oops, sorry, was that it, Joy? Okay, yeah.
That's it.
That was the eliminated slide we're working, we have data on that. We just started that. I had a slide as a future, one of our future tasks, and I took that slide out. The data we have, I don't think we have any 4 lanes, for beer on here or anyone, but we do have data. We've collected data on some heavier traffic 4-lane roads around the university. So the answer is, we don't know yet, but we're hoping. Come back, maybe in 2 months we'll have that processed.
Okay, do you consider that it is viable to carry out the video processing by using an embedded system such as NVIDIA, Jetson, Xavier, NX in the bus and transmit the volume data to the cloud?
That, I should look at who the participants, I don't know if like Christoph or Keith Redmill or Ben Koifman are on it. They'd have to answer that. I don't know the how that's going to work from the processing side. Any of those guys on here?
Well,
No,
this
Ben. Oh, there's Christoph. Hi, Christoph.
I mean, this is something we're looking at, using the computers which is already on the bus to do the calculation. It looks like it's going to be possible. So I don't know about Xavier, but probably with Xavier one can do that.
Hi, Mark. This is Keith. I don't know if you can hear me or not, but yes, I'm inclined to think that some embedded NVIDIA hardware would be able to do the processing on board if one wanted to do that and save the downloading of the video itself, which is, as you know, a time-consuming and annoying process sometimes.
Yeah, so I appreciate Keith and Christoph on that, and not to sound like a politician or punting. My feeling is, if we can show that the information is valuable, like we can get good traffic estimates, someone's going to come along and figure out how to process it. I think it's feasible, just because people always make advances in that. It's just, are people going to put their efforts into it? But maybe I'm being a little bit of a cheerleader here. So
We have a lot of cell phone data on traffic volumes from companies such as INRIX and MoveIt. What is the advantage of cameras on buses or road tubes now that we have this capability?
That's something we're talking about. I'm going to punt and say I'm not an expert, in case someone in here is an expert. My limited knowledge is those have not been validated. They're a bit selective, less selective than they used to be. And it's not clear how they work really well in urban areas. But that's definitely something. I don't know. I don't want a promoter of them, but if someone, we've talked about that in our group, and we just think this would be a more objective approach, whether the advantage of sort of the less bias in terms of where we're getting data from outweighs the additional effort or not. I don't know, but that's sort of our team's line now until we see the validation of those are on our team, not me, but other people have used INRIX, and they say, okay, it's good, but there are some biases in there. Anyone in the audience want to add to that? Street light, et cetera, are things that are coming out, but again, they're selling repackaged data, and it's not clear. We're trying to get some to sort of compare also, by the way, but I don't want, that's not sort of in the next 2 months like these other elements we're talking about.
Okay, this method works by observing the vehicles passing the bus in the opposite direction. How would it work on one-way streets?
Good point. It wouldn't. At least the method we have now would not.
Can we get an estimate?
I'm embarrassed. That's one of those. Boy, I never really thought of that, because some of the downtown streets are one way. Now there are ways, of course. Well, I shouldn't say of course, but there are ways with the traditional moving observer where you look at how many vehicles overtake you, and But I think that would be a different approach. I mean, it's the same concept. We haven't gotten there yet. But that's one. I'm embarrassed I hadn't really even thought of that. Yeah.
Okay, can we get an estimate of flow at a point in space from this method?
Estimate of flow from a point in space. I don't see it right now. Ben Koifman, who's on the team, likes to, generalize flow and time, space. I know a little bit, not even enough to be dangerous. I don't see it now. Ben wasn't sure he could make it. You're not on, Ben? I don't see it right now. Doesn't mean that a new, you couldn't, Ben would tell you we could get it from the data somehow. But the question, I don't think using the simple approach that we're using now for time of day volume on a segment, I don't think that would give it at a point in space. So our focus is sort of on the traditional traffic engineering. I have this segment that I'm trying to estimate flow on. And I know the theoreticians like, points in space, but that's really not of, I can't see that of being too much interest other than theoretical in an urban network. For again, surface streets, we're not talking about interstates cutting through town. We can get those estimates pretty well.
Okay, that is all the questions that I have.
Okay, well, I'd like to thank good questions. People always have good questions, but they're thought-provoking questions. Thanks for that. Thanks for everyone's attention. Thanks, Joy and Lisa Kay, for putting this on. Do I just sign off or?
We will sign you off. Thank you so much for sharing your work, Mark. And to all of today's attendees, thank you for joining us. As I mentioned earlier, today's presentation will be posted on the Mobility 21 What's Happening page of the website, along with a link to the video of the session. This afternoon, you will be receiving an email asking you to take a short survey about today's SMC. Please take a few minutes to provide your feedback. For students who are interested in engaging in transportation topics, the Transportation Club on campus is a great way to plug into transportation topics with fellow transport nerds. Again, thanks for attending today, and please feel free to contact us with any questions.